To prove that the optimum launching angle is 45 degrees, I first think of an arbitrary situation here. If I fire a projectile with a velocity of u at an angle of theta, I'm going to have its two components, the ux, initial velocity x, and uy, and I can break them into their components there. So u of x is going to be u cos theta, and u of y is going to be u sine theta. The other thing to consider is because acceleration only acts in the y direction, we assume this has no air resistance. Acceleration, therefore, is just minus g because it's pulling downwards. So I define the direction as down, that's negative. So a is negative g. The first thing we want to consider in this proof is the time of flight. So I'll use the equation s equals ut plus a half at squared. Now there's a few things here that I'm going to substitute. Because we're talking about time, the flight time is how long it takes to get up, how long it takes to get down. That's how we measure it. So s is going to be u, which we're talking about the y direction, right? So it's going to be u sine theta plus a half, and a we said before is minus g, and t squared. So I can tidy this up a little bit. It's going to be equal to u sine theta t minus g on 2t squared. And this is equal to my distance. So first things first, I can substitute out a t. So let's try and factorize this a little bit. So if I pull a t out the front, I get u sine theta minus g t over 2. Now there's a thing in maths called the null factor law, and that tells me that if two things are multiplied and they equal 0, then either one equals 0 or the other equals 0. And why that's useful is because if I consider that this equation is telling me the distance, if I want distance to be 0, I'm on the ground. So there's two ways I'm on the ground. Either I'm on the ground because I haven't started, or I'm on the ground because I've fired, turned around and come back and hit the ground. So let's say distance equals 0. I'm at distance 0, I'm on the ground. Now I have t times this equals 0. So using the null factor law, there are two options. Either t equals 0 or all of this in the brackets equals 0. T equals 0 is not particularly useful because time equals 0 is arbitrary. It's just like saying, well, yeah, you're going to be on the ground before you've even fired the rocket. Well, of course you are. So that's useless. If I consider the other half, however, I get 0 equals u sine theta minus gt over 2. And now, remember, I'm trying to find time. So I just solve this for t. I'll put the u sine theta over here, which will become a negative. I can times by 2, so I'll get 2u sine theta. I'll divide by g, and I'm left with time. I've got a negative on a negative, so those can just cancel out. I get back a sweet positive fraction, and I've got my expression for time now. So time is equal to 2u sine theta over g. And that may seem kind of useless at this point, but this is my expression. So for some arbitrary situation, the time of flight is going to be equal to 2 times the initial velocity times sine theta divided by g. Now the second part that I want to consider is the range. So I've got my expression for time. Now I want to think about how far does this travel. If I know the time that it flies for, I can calculate how far it travels. I'm going to use the same equation, except that the plus half at squared is going to be 0, because remember, acceleration in the horizontal component is 0. There's no air resistance. So all I'm left with is this. my x component velocity times time. So distance traveled is just velocity times time. But I know these two now. Ux is u cos theta. And t, I just found, is 2u sine theta on g. So 2u sine theta over g. So I just substitute those in, and now I've got an expression for s. If I expand out these brackets, I'm going to get u squared from these two. I'll have a 2 sine theta cos theta, and that's all going to be divided by g. That's going to be my range. Important thing to note here is that 2 sine theta cos theta, if I write that out, 2 sine theta cos theta, using the math identity, that's actually equal to sine of 2 theta. So I can simplify that even further. So that's going to mean that my distance, my range, is u squared sine of 2 theta divided by g. So now I've got range in terms of my initial velocity, my angle, and gravity. But if you think about it, gravity is constant, so we can't change that to get a better launch position. U is basically arbitrary because we've just said it's any velocity we want. So it doesn't matter what we do to that. We know that if it gets bigger, the range will get bigger, but that doesn't tell us anything about the angle. So really, theta here is the only variable in this situation. This depends on the theta. So if I want to think about this in terms of proportionality, u squared is directly proportional to s. So if this increases, the range will increase. G is inversely proportional. So if I could somehow reduce gravity, yep, I'll go further, but I can't do it. And sine of 2 theta is directly proportional to the range. So if sine of 2 theta gets really big, s gets really big. So the question becomes, when is sine of 2 theta the maximum? What is the maximum value for sine 2 theta? If you picture a unit circle, remember that cos is basically your x component of any angle, and sine is your y component of any angle. At what point and what is the value at which sine of 2 theta is the largest? Well, the largest possible value that sine can ever have is 1. So therefore, we say that sine of 2 theta equals 1 to get the maximum. So that's the maximum value, sine of 2 theta. So I just solve for this. So if I want theta, I then do, in my calculator, I do the sine to the minus 1, the inverse sine. And that's going to equal 2 theta. Very important here to ensure that you are in degrees. Because if you were in radians, the calculator is going to give you pi on 2, and it's going to give it to you in decimal places, and it's going to be really weird. Your answer won't make any sense. So it's really important that you're in degrees. If you're in degrees, sine to the negative 1, inverse sine of 1, is 90 degrees. This angle here, 90 degrees, gives me the maximum value of 1. So 90 degrees equals my 2 theta. Therefore, theta is obviously equal to half of that, equals 45 degrees. And this is what I wanted to prove in the first place. So for any value of u, initial velocity, to get the optimum range, the angle that I need to fire from is 45 degrees.